Okay, thank you so much for coming. It's early Monday morning. You're all really tough. Yeah, so we're already in the 10th week of topology. So this week, the assignment will go online, and you have to hand it in next week. Hopefully, it's fairly harmless. So my plan is still that everyone passes. So we'll see how that goes. But today, let me remind you of what we have seen last time, because it is just really, really important. So I just copied it from the other slide, and I put it on one slide, essentially. So there's this one theorem, and then there is a specific form a surface has, which we call the standard form. And as soon as the surface is in standard form, and I'm kind of getting a bit annoyed by the noise. Give me a second. Okay. As soon as the surface is in standard form, we can uniquely identify it, and that's the whole point, right? So as soon as you have it in front of you in standard form, you know essentially everything about it. And the standard form, there are only two standard forms. So the top one, which is a lot of tori, which are illustrated as little handles on a sphere and kind of pokes holes in the sphere. And the bottom one is a lot of projective planes, which I really can't illustrate, so they look a bit strange, but we hopefully get used to it. A little bit dangerous, like a lot of red and greenish colors, if green counts as dangerous. Anyway, and then there was also holes. Okay, and what we always want to count is those numbers d, p, and t, and because there are only two standard forms, either p is 0 or t is 0. Yeah? And we kind of want to decide, as soon as you see a surface, you kind of want to decide whether t is 0, whether p is 0, and how many of the others do we have. And that was just really, well, this one theorem kind of summarizes everything. And this is obviously like really, really important. And let me pull this up again because somehow it's a bit confusing. So the left-hand side is not in standard form because there are handles and projective planes. And as soon as you have both of them together, you can essentially take the torus and replace it by two copies of the projective plane. So you always have kind of this equation that t equals 2p. So I called this last time that the projective plane kind of dominates everything. As soon as you have one of them, it kind of will eat up everything. And that's exactly the reason why we want to have some standard form, because these are the two same surfaces, but they look different if you just look at the pictures. And that's why we don't call the left one a standard form, we only call the right one a standard form. And remember, this came from my analogy of that this is like a prime number decomposition, but then there is this flaw that it's not quite unique. There's this non-uniqueness because the projective plane just eats a torus and spits out a Klein bottle, and we fix it by just getting rid of all tori as soon as we can. And I hopefully don't need to tell you that this kind of theorem is like really important. It's essentially the main theorem about surfaces. It gives us a complete list. So the whole point of classifications is always that you want to write down a list of things, and this is a list, essentially. So you can just list them on a piece of paper. They're infinitely many, but you know what I mean. Okay, so what we have in mind now is we kind of wrap up a little bit what we have seen about surfaces, and then we turn back to graphs and surfaces together, which is a really cute topic. But we won't see that today. We'll do that next time. We just wrap up, and I remind you how to do the calculation. If you look at the polygon, how to get the standard form. So that's kind of the main goal. If you look at the polygon is nice, polygon is easy to write down, but there is some ambiguity in the polygon because several polygons can represent the same surface, so we always want to bring it in standard form. And something that is really powerful, kind of really combinatorial and very nice, is a word that we associate to a polygon. And a word is really just a concatenation of symbols. You see that in a second. So by a word, I really just mean put symbols in a row. And what I will do, I guess I do it like this, is if I have a polygon, okay, like here, and the kind of the standard question should be, what surface is it? So where is it on our list? Yeah? So where is it on our list? And we want to figure that out. And the good way of doing that, the first step is always to write down the word associated to it. And this is how it works. It's kind of really easy. You start somewhere. Let's say you start here. Okay, so you start at the North Pole. And we have some convention how to read along the surface. And I'm always reading counterclockwise. So I'm reading in this direction along the surface. And I just collect what I see. So I see an A. So I write an A. So I see an A here. So I write an A here. Right? So just write an A. I continue. The next edge I hit is a D. So I see a little d, so I write my little d here. And the next edge is a b, so I write a b. And the next edge is an I, so I write an I. And the next edge is a d in the opposite direction, and I write a d with a bar for it. Right? The bar just means it points in the opposite direction. So d bar, c bar, b bar, and so on. And just continue around until you're back to A. And it gives you a word, so all the way around, dot, 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 until you hit G, which is kind of the final letter here. And we can read off surprisingly a lot from the word. Okay? So we can, for example, see how many edges we have. It's just the number of symbols in the word. So here it goes from A to I. So if I is the 9th letter in the alphabet, and I haven't messed up, there should be 9 edges. And just read the letters you see. So here we immediately get number of edges if I'm not miscalculating. So I is the 9th letter, so its number is 9. Number of faces in this case is easy anyway, and only the vertices are always a bit tricky. But we can read off a bit more. So we can, let me just go one step further, then it goes away. This is just repeating what I just said, just writing down the convention. Depending on the orientation you see while you walk along, you write a bar or not. Fine. But we can read off the following, for example. So maybe I find a good example here. So G and G turn up in the same walking direction because they are both G and G. So you immediately know that this surface is non-orientable. Yeah? So you immediately know, if you see something like this, that P is 0, T is 0. So P is not 0, which means orientable. It's always a bit confusing. T is 0 is non-orientable. We have no tori. Okay, and you can read it off immediately from the word because we found a pair G. I could have alternatively found the pair I, for example. So any pair is fine. Any pair that points in the same direction is fine. Okay, and you can immediately read off from the word that the surface is non-orientable. It's kind of a really powerful way to encode the word. And there's a convention involved, so I'm already reading anti-clockwise. Okay, fine. You could read the other way around. At least make sure that whoever your reader is, they know what you're talking about. So I always read kind of this way around. Kind of the standard way in mathematics. The standard way in mathematics is always anti-clockwise. I don't know why, but that's what it is. I hope that's reasonably clear. It's kind of nice, right? You just read off a word, and the word encodes quite a lot of information already about the surface. And that's another kind of step of reduction. So the polygon is a two-dimensional object, but the word is somewhat just a line, if you want, just a string. So it's in some sense a one-dimensional object. So it's a reduction of the problem to a slightly smaller thing. Okay, so let's do it. So why not? And you will see that you can somewhat eyeball what surface you have if you just know the word. You just need to know a few patterns. Okay. So if I start reading here and I go around, I will see A and A bar, right? That's just what I will see, A and A bar. That's our friend, the sphere, and you will see the pattern AA bar somewhat corresponds to a sphere. So that's what I'm trying to tell you here. For this guy, maybe not quite our friend, but anyway, if you read along like this, what do you see? You also see A and another A, but in this case it's AA, right? So it's AA instead of A and A bar. So the AA pattern, the non-orientability pattern, corresponds nicely to a projective plane. And whether you see AA or A bar, that doesn't matter, that's a convention. So as soon as you see the two point in the same direction, you essentially have found the projective plane in your surface. Okay, let's do one more. So the disk is the one with AB in any direction. So again, I hope this is pretty clear. If I read around like this, that was really bad because now I cut my own picture. If I read around like this, we get AB, right? And just let's continue with the standard surfaces. So we have them written down on one slide. Let me be a bit faster. Let me just pull them all up. Okay, so annulus, Möbius strip, torus, and Klein bottle. And you kind of can see the difference between them, right? If you just really carefully look at the symbols. So annulus and Möbius strip are not really that different. One of them is glued together like this, and the other one is glued together with a twist. And you can see the twist in the polygon decomposition, in the word, because this one gets a BB, while this one gets a B bar. Right? So letters of the same or in the same direction, so B and B or B bar, for example, they encode that you have a twist somewhere. Right? So that's what I'm saying. Similarly for the torus is twist free. So here's the pattern for the torus. Something you should remember somehow. So AB, A bar, B bar. Whenever you see such a pattern, then there's a torus somewhere in your surface. And in contrast, the Klein bottle has one twisted, because it's exactly the annulus, right? And then you twist it when you glue the two ends together. And you can see that directly. There's an A and an A in the surface. And that's a really, really efficient way. And these are kind of the standard patterns. So whenever you see them somewhere, you should be like, there's a projective plane in my surface, or whatever, there's a torus in my surface, something like this. And we'll play that game now, and it's a kind of really efficient way of writing down a polygon. Okay. That's what I already said, but I want it on the slide anyway. Looking for those letters, AA or A bar, for any kind of label, A could be I or G or whatever. As soon as you find one of them, it's non-orientable. It's a very powerful way to just read of orientability. As soon as you have one, it's non-orientable. The projective plane dominates. You have found a projective plane in your surface. The AA pattern is a projective plane, so that forces everything to be non-orientable. It's a really, really powerful way to read of orientability. Yeah, okay, that's just what I just said. So really just the first thing you do, if you see a surface, write down its, if you see a polygon, write down its word. Just a reminder so that nobody gets confused. There's something a little bit strange with the words, but it will be kind of clear if I go back to the picture, if I just draw another picture. So here's my polygon, yeah? And there are some edges in the polygon, whatever, something pointing in some direction, God knows what it is, and I'm reading like this. Okay, so in doing so, I'm choosing a start point. Let's say I start here, and I see the edge A. But that's just, again, the convention. I could start everywhere, and my word gets cyclically permuted. I'll show you some examples in a second. You'll see that in a second. So I could have started here, and then the A comes way later, or I could have started here, and it comes even later. So kind of the start point, I have a circle, right? So the start point on the circle, that's kind of a weird notion, because the circle has no preferred point anywhere. And I just choose one and read from there onwards. And this is only well defined up to what is called cyclic permutation, and cyclic just means you go around the circle. I'll show you an explicit example in a second. Okay. So here's an example. So all of these are all patterns for the torus. So let's have a look at them. So the first one is the one I showed you. So let me write down the torus again. So A, B, A, B, and then it goes in the opposite direction. So A bar, and in the opposite direction, so B bar. Okay, and now what I did in the first word, for the red word, I start here and I read around. For the word next to it, I can give it a label, I will give it a whatever. What is nice here, maybe orange. For the orange word, I start here and read around. But it's still the same polygon, and so on. Right, so they're only defined up to rotate. Think of them as sitting on a necklace, and you put one of them around. It's a different word, but they represent the same surface. So if you keep that little ambiguity in mind, you can essentially read off the surface from the word. And that's what we are trying to do now, which is an even more efficient way of encoding surfaces, just as little strings of symbols. No? So BA, and then all is also only well defined up to reordering. So let me just draw it again. So this is also the torus. If I just redirect all edges, it's also the torus. Yeah? B, B, A, A. Because essentially we only use the orientations to glue things together. But if you change both orientations at the same time, the gluing just turns around and it's still the same gluing. You just kind of turn your head around. And then you get the other patterns, for example, B, A, B bar, A bar, whatever, if you read around here. So let me do it. So here, if I read around, I get A bar, B bar, A, B, which is this little word here. And that's all you're allowed to do. Right? So you're allowed to, it lives on a necklace, so you're allowed to turn it around, and you're allowed to swap orientations always for both words at the same time. So if you swap B, you also swap B bar. And you get different words representing the same torus. And all of these 8 pictures are kind of, whenever you see them somewhere, you can be sure that there is a torus in your surface. So this A, B, A bar, B bar pattern, in whatever order, is always torus. Okay. I skipped that part. So what we want to do is I want to write down standard words. Standard words for the standard form of a surface. So what I need to tell you is what are the standard words for our prime factors, right? That's essentially what I need to do. So what were our prime factors? Well, there was a torus, there's a projective plane, and there's a disk. So I will show you the standard words for those. Okay. Hopefully this pattern is by now reasonably clear. So the AB, A bar, B bar pattern. Okay, and if you do it twice, well, that's exactly what I said. You see here this guy, and you can see the torus in your picture. Here's a torus. Similarly, you see this pattern, and there's a torus in your picture. And that's why this is a double torus. So here's a torus, a red torus, and here's a green torus. So the hash sum, in this case, is really simple. You just take the word and stack it to itself. You just need to relabel the edges to make sense of it. And maybe you can already guess what the third one is. Let me mark the tori again. So here is the first torus, the same pattern. Here is the second torus, kind of same pattern. So maybe I should mark them here as well. So here's this one, and maybe purple for the last one. Is the final torus. So it's really easy to describe them now. Third hash, fourth hash, fifth hash. It's just a word with always the same pattern, just those 4 symbols corresponding to a torus, and then just stack them in a row. And this is what we call the standard word for the torus. It's always, well, this pattern, AI, BI, AI bar, BI bar. Just repeated T times if you see T of them. And it's really always, here's a torus, here's a torus, here's a torus. This one is cool. So this one is really nice. And yeah, so if you see a surface which has one of these patterns, there's a torus inside, which makes your calculation somehow already easier because you already identified a torus, which is one of our basic pieces. Turns out that the projective plane, the one that is always a bit scary, is like super easy on words. So here comes something really remarkable. On words, the projective plane is like really simple. And that's why it's so easy to read off non-orientability. You only need to ever watch out for this pattern. Okay. Here's the projective plane. If you do it twice, it's really easy to spot. It's really just A, A, B, B. So here's my first projective plane, and here's my second projective plane, and they're nicely hashed together. So the pattern is A, A, B, B. And you can probably already guess how this continues. So A, A, B, B, C, C. Projective planes are like really simple. So here's my first projective plane. Here's my second projective plane. and here's my third projective plane. Okay. So whenever you see any of those, it's a projective plane. So AA or A bar, A bar. And you probably have guessed the general pattern. It's really simple. It's just extremely simple. So it's kind of remarkable that the projective plane, which is kind of so difficult as the surface itself, is kind of really simple as a polygon, and also kind of really simple as a word, right? It's just AA, BB, CC, DD, EE. Okay. So here was the standard form of the torus, and here is the standard form of kind of projective planes. So one is missing, the standard form of the disk. And kind of, again, very interesting. So the surface that is the most difficult, the projective plane, has the easiest type of presentation as a polygon or as a word, just this AABB pattern. And the surface that is the easiest, the disk, has the most difficult presentation as a word, and also as a polygon, which is kind of really strange and really remarkable. But we need to do it, so let's just do it. Let's just do the disk. Okay, so we want the disk. The first one is, well, this one. Fine. But the second one is already a bit tricky. Okay, but I do it for you. So we want to hash this guy together, and what is it? It's not so clear. I'll show you how it works. Just the point why this is so difficult is that the first naive guess is not correct, because this has boundary. And you need to be careful where you actually put your little bridge between them. So for all the others, you just stack them together and that's fine. Here you need to be a bit more careful. So this is wrong. This is not true. Okay? So for all the others, let's go back. Let's just do the projective plane. For all the others, it's just stack pattern next to pattern. Stack pattern next to pattern. So if you hash a torus to something, you can just stack it along. If you hash a projective plane to something, you just stack it along. But for this one, it's not the case. So it's not true. And that's why this gets a bit trickier. So let's do it. So what you need to do is the following. You need to cut in a little bit. You need to separate the new edge you want to use from the old edges. That's the whole point. So I cut them in, bend them open, so the edge E is now here, and then I can put in a new edge. So note here the following. So here's a hash, which is saying, maybe this is a bad color here, maybe green is better. This is a hash, which is saying I still need to put them together. And now my hash is gone, so no hash anymore, because they are already put together along G. Okay. So what I've done here, instead of stacking them together, that doesn't work if you have a boundary component. You need to cut in once, open it a little bit up, and then you can glue in the extra edge G. So the G is the hash edge here. So the hash is our little G here. So put in the extra hash, right? So now we could exit along G, and you can enter along G at the other point. And now we can just glue it together again. It will be this, right? So I just put them together along G. So the top one is, let me mark it. So here's the green one, right? This is this one. Just glued together along. Maybe there's a good color here. Maybe this one. This one is a really awful color. Maybe this one. I just glued them together along G. Yeah? So at the bottom, you have this pattern. And now you can see why I've done this. So now I have those paired edges F. What is a good color? Maybe this one. F and E here in the middle, and I've separated the original disks. So this is my original disk here, this one. And the other one, maybe yellow. Yellow is a horrible color. But anyway, the other one is this one. So I've separated them by gluing in this extra piece of junk. And I need to do that because otherwise, if you just think of it, what happens, so what we want to do is the following. We want to take them and we want to put a little bridge between them. Right? That's exactly the hash operation. But if I don't pull in something, I will put this little disk too close to the boundary and my picture gets wrong. So if I don't do that, then actually my little disk here would be somewhere here along the boundary, and this is not what I want. And that's why this one gets a little bit more complicated. Anyway, we can now simplify and read off the pattern. That's all we want to know. Okay. Good. So this is, and you can see now that it's separated. So what is happening here in the last step? I just take those two edges and I call them together A So they're both these ones. I take those two edges and call them C, and I take those two edges together and call them E, and the same point at the other side as well. And you can see now it's now separated. So maybe I go one further. No, it's already gone. Maybe I just park this somewhere else for a second. So it's separated. So here, this is an X edge, vertex X, and it appears on the other side. So the C is just doing a little loop around X. So this is like C. And let's say the top edge, top vertex is Y, Y. So now I have my little A looping around Y. So they're separated, and that's exactly what I need to do in the hash product. And that's why this is a little bit more complicated than the others. Okay, fine. Let me pull this one back to where it was, something like this. And this is why this gets a bit more complicated. But I'll show you on the next slide the standard word, which is not so bad. But in order to get it, you need to do these manipulations, while for the torus and the projective plane, which look more complicated, you just stack everything together. So it's kind of much, much easier. Okay. So this one is always a bit tricky. Okay, and if you do it 3 times, you just do the same. You cut them in. You need to create this extra cutting in. You pull them out, and I just rearranged it, and you get this one. So I just skipped one step compared to last time, and there's this edge I now, but you have F and G and the same type of pattern, and you have, what is it? This guy here is this guy here, and where is my friend? It's here, is here, right? I just put in some junk in the middle, and then you simplify exactly in the same way by identifying everything together, and you get this type of pattern, which is really just an edge A. So here is a free edge. Here, maybe I use the same colors. So is a free edge, and our little E is free. And then there's some things glued in between to kind of separate them. They're not allowed to be in a row, because then they're one component. So I separated them using those little edges here. Okay. So rid it of A, B, whatever. A, B, C, F, E, F inverse, B inverse. Okay. And it turns out that this is the pattern. So it's not so bad in the end, but proving it is a little bit of a pain. You just do this operation kind of recursively. So the pattern is you do A1, B1, A2, B2, whatever, up to B, D minus 1, AD, and then you read the B's backwards. Okay, not so bad. So A1, B1, the B1s are always the edges that I put in to separate. So these guys are the various disk parts. This one, this one, this one, so I should have D of them. And the other ones kind of belong together. So this one, and this one, this one, and this one, and so on. They are stuck there to separate the various edges. So this is the pattern for the disk. Okay. So let's go back. Just have all patterns again. Too many slides. Where are we? Somewhere here. Okay, the torus pattern. The torus pattern is 4 symbols: A, B, A inverse, B inverse, or A bar, B bar, and then just stack them arbitrary many times. Yeah? It's really the basic is here 4 symbols, and stack them arbitrary many times. Okay. The projective plane, like really simple. Didn't I have color? No, so let's add color. So here, here, and maybe purple, and really just 2 symbols, AA, and just stack them, concatenate them nicely together. Really simple, so you can always read off projective planes easily. And then the final one, and that one is tricky, and it should tell you that reading of boundary components should be the most difficult part of identifying the surface. And if you have done some of the exercises, it definitely is the most complicated part of identifying the surface. And you can already see it in the word, because the word is not just copying a certain string 15 times, but it's somehow more delicate, right? It has this interlacing patterns between the edges I glue in the middle and my real boundary components. So if that is true, then there should be an order of difficulty. Finding the boundary disk should be somehow the most difficult task, and it somewhat is. And finding orientability or deciding orientability or not should be really simple, and it definitely is. You can see the hierarchy of difficulty in the words. And it's kind of exciting or kind of really strange, whatever you want, because the most difficult surface, I say it again, has kind of the easiest appearance, because it's somehow so difficult it kind of absorbs everything and you can always tell where it is if you want. And the kind of the easiest one, the disk, is kind of very subtly glued into your surface. Kind of very interesting to see. Okay. And now comes the game, and we will just play it. So I could ask some question like this. So what standard surface is given by the following word? Okay, AD, whatever. You can read it up here. And the first thing we do is we just draw it. And now we do this very slowly together. So we just draw it. I hope I haven't messed up, so let's check. So we start by reading here, and we read along. So let's see. I see ADB C bar, E C bar, F bar, D, H, G, E, A bar, and H. Well, now that's my polygon for the word. And you really just get it by writing down the edges. It's not really difficult, right? You start somewhere, put the A, put the D, put the B, put the C inverse, and so on. Just do it. Okay. And as soon as that's written down, the first thing you do is you check whether it's orientable or not. And that's really simple because you only need to look for a pair, so let's try it. I can already spot one. So here's C, for example. C is the projective plane. So we can see it here. There you go. In the pattern, there's projective plane. I could see a few more. So H is, for example, also a projective plane. So there's H. The E, I can also see the E. But you only need to find one. You don't need to find all of them. But anyway, you find one, let's say C, and you can already write down that T is 0. Okay? Wasn't so bad. So you can already tell from here that T is 0. First step, fairly easy. Okay? T is already 0. The next thing we do is we identify the vertices. And I've done that already, but let's just do it at least for X. So what you do is you start marking one of them. So let's say you mark this point X, and then you follow it. So X sits at the top of H, so it sits at the top of H. It sits at the bottom of G, but G doesn't go anywhere anymore, so we are done in that direction. But it sits also at the bottom of A, so we jump to the bottom of A, and then it sits at the bottom of, at the tail of H, we jump to H, then we jump to D, and B doesn't get anywhere anymore, so that's our track of X, right? So, and we do the same with Y and Z until we are done. Okay, so first step, identify orientability, easy, just read it off. Yeah? Essentially just really read it off. Kind of, again, the projective planes are so dominant, if there's one, you won't miss it. Okay. Then you mark the edges, sorry, the vertices, and you will just write it down. So now we can count. I see vertex X, I see vertex Y, and I see vertex Z. So we know that the number of vertices is 3. Okay. From the word, we can immediately read off the number of edges. Why? Because it's just the number of symbols, and it counts up to H. So A, B, C, D, E, F, G, and H. So if I'm not miscalculating, so if you just walk around here, then the number of edges should be 8. Yeah, so here's 8, here's 3, and the face is always easy, it just stares at you, So the number of faces, what is a good color? Maybe orange. Number of faces is 1. And if I haven't messed up, then the Euler characteristic is -4. Okay. So we already know t equals 0. We already know that one. And we know that the Euler characteristic is -4. So let's do the boundary components. Okay. So how do we read off the boundary? It works as follows. You write down the 3 edges, the ones that are not paired. If I haven't messed up, it's B, G, and F. Okay. A is paired, you can see it. C is paired, you can see 2 C's. You can see 2 D's. I see 2 E's. And I see 2 H's as well. So B, G, and F are exactly the 3 edges. And now we just need to do the following. I guess I need some space. So let me jump back to here. I just write down X, Y, and Z. So these are our 3 points. Right? We already identified them. And let's have a look what the edges do. So the edge B, my blue one, jumps from X to Y. So it jumps from X to Y. I put it here. The what is it? The purple one, or light purple one, G, jumps from X to Z. So I just put it in. It jumps from X to Z. Very good. And then there's one remaining. It's kind of this brownish color. Do I actually have that one? Let us approximate the brownish color with black. So the edge F goes from Y to Z. It goes from Y to Z. So they nicely, so this was F, this was G, I think. Let's double check. This was G, and this is B. So they nicely form one circle, and you can just see it by just putting the vertices on an extra page and just filling in the edges. So they form one circle. So I have one boundary circle. So we get D equals 1. Okay, as I claim down here. So this works out as well. D equals 1. Very good. So we have already almost everything, right? We only need to know P. So we have almost everything. So let's do it. Maybe here's some space. No? Okay. Let's try on this page. Let's move this a little bit to the side. Because we have this formula, the chi of the surface is the magic number 2, which always appears, minus D minus P minus 2T. Okay, now we can just solve. So let's do it. So D is 1. So this is minus 1. We already know that T is 0. So this is 0. I forgot what chi is, but it's on the previous slide. Was it minus 4? It's minus 4. Okay, minus 4. So we have the equation minus 4 equals 2 minus 1 minus P. And we can solve for P. So P is 5, if I'm not miscalculating. Really just solve for P. Yeah? Hopefully you will see it's 5. And then we are done. Then we can write it down. We have P, so check. Let me just write it down here as well. P is 5. Very good. Check. P is 5. And that's our surface. We have 1D. We have 5P. There you go. It's this guy. So we can just write down. We're done, right? So that's what we wanted to do. And we can just write down the standard form. So let's just do it. So 5 times the projective plane is hopefully not so difficult. So it's BB, CC, DD, EE, FF. Yeah? And then, well, one boundary component, so it's A. Okay, and from here we know everything. It's exactly the surface which has 5 projective planes. Okay. It's kind of magic. So it's not difficult, and you can always, well, it is confusing. You need to do it several times yourself. That's just how combinatorial. That's like life in general. Practice makes perfect. You just need to do it. But compared to what we had like last week, this is just really fantastic, right? So maybe I just repeat it in words what we do. So the first thing to check is always whether it's orientable or not. And that's usually very easy. Read along and look for those non-oriented edges. you only need to find one of them, and it's already not orientable. So it's a 0, 1 question. So you either have t equals 0 or you have p equals 0. Okay, then calculate the Euler characteristic. Most difficult step is usually to find the vertices. And as soon as you have them, it's just counting 3 vertices, 8 edges, and 1 face, and you get the Euler characteristic. And the boundary cycles are then also easy to do, and my way of usually doing it is really this picture, to just write down the vertices and connect the various edges into the picture, and you will see cycles. You could see 2 cycles. Maybe I do another example in a second, but in this case, there's just 1 cycle. So you write down d equals 1. And then you're essentially done. The rest is just solve this equation, which is crucial, which you somehow should try to remember. Just solve this equation for whatever the remaining variable is. So we already identified 3 out of 4 variables, so you can just solve for the remaining one. And this gives an algorithm to write down the surface. So let me try to find some space, and I do just another one for you with 2 boundary components. So usually a good practice, I can tell you how I generate those pictures. So there's some code that I'm using, and essentially I just give it some symbols and it will generate those pictures. So essentially I just type a random sequence of symbols, namely A, B, C in some order, and it will generate those pictures. And a really good way of kind of generating examples for you to try yourself is just to write down a random word. That's essentially what I'm doing as well, and then go for identify the surface. That's essentially what will happen for the exam as well. So I'm typing in a random word, it will generate, and not too large random word obviously, it will generate a surface, and then I will ask identify the surface. So it might make sense to just test it, try that yourself. Practice makes perfect, like 2 or 3 times. So let's do one. Okay, I could do something like A, B, this is supposed to be a B, maybe C, maybe a B again. Something like that. Okay. Maybe you already know what kind of surface it is. Maybe not. So let's try to identify it. So I see A, B, C, and B bar. So it's orientable. It's immediately orientable. Okay. So I write down P is 0. Okay. So then I start, like, say, as this edge is X, and I follow it. It's the bottom of B. So it appears here as well. Here's X. And then this is edge is Y. It's the top of B, so it appears here as well. So that's Y. So my Euler characteristic has 2 vertices and has A, B, C, 3 edges and 1 face. So my Euler characteristic chi is equal to 2 minus 3 plus 1, which, if I'm not mistaken, is 0. Fine. Good. So within 30 seconds, let's say a minute or 2 minutes, whatever, doesn't really matter, you've already identified 2 crucial components. Okay, and now we can just do the same trick. I list my X and my Y, and I look at the 3 edges. So this edge is free and this edge is free. So A goes from X to X, so it does a little loop here on X. And C goes from Y to Y, so it does a little loop here on Y. Right? So now you see 2 cycles. So you write down D is 2. D is 2. So there's 2 cycles. P is 0, D is 2, and we have identified chi, so we can just solve for t. So let's solve for t. So we know that 0, chi equals 2 minus D minus P, P is 0, minus 2t. So it looks to me like, so those 2 cancel, 0. 0 equals 0 minus 2t. So I hope, if I haven't messed up, t is 0, and we have identified our surface as being a twice punctured disk. Okay. Which hopefully is not a surprise, because what I've drawn is an annulus. Right? So if you just identify those, you see the annulus. I was just running the algorithm for you. Okay. And as I said, it's a really good practice to just do what I just done. Just write down a random sequence and just run it. Run it 3 or 4 times, and you will think this is just a piece of cake, which is the whole point of this discussion, that we have now really wrapped up the whole story, and there's a very explicit algorithm that you can always run. It will always work. You can do it on multiple components if you like, and it will always get you there, and it will always tell us the standard form of the surface. Okay, so let me pull it up once more, and then we are good for the next topic, which I will just do next time, right? So we want to identify the standard surfaces, and today I showed you kind of an algorithm to do it. And with any kind of combinatorial gadget, you just need to run it yourself a few times. Okay, thank you so much for coming today, and I hope to see you Thursday.